Hello, everyone. Welcome to today's webinar. My name is Wyatt Pena, and I'm the President of Operations here at Ridgetop Group. Today, I'm joined with one of our battery simulation engineers, Dr. Vasav Goswami, and together we'll be presenting an in-depth look at our collection of battery health modeling, simulation, and analysis software tools, or MS&A for short. During this session, we'll explore the capabilities of the advanced electrolyte model, CellSage, and our adaptive remaining useful life estimation software. Together, these tools have been developed in collaboration and partnership with Idaho National Laboratory for the purpose of advancing lithium-ion battery research for unique applications. We greatly appreciate your participation in today's webinar, and we kindly ask that you hold your questions until the end, and we'll address them during a Q&A session. Afterwards, we'll be sure to provide the slides and the webinar recording to all registered attendees once it is uploaded to our YouTube channel. For today's agenda, we'll start out with a brief overview on Ridgetop Group and our background with Idaho National Laboratory. We'll cover the importance of battery health modeling and simulation analysis software tools and how they advance lithium-ion battery research. We'll provide a technology overview for the advanced electrolyte model, a technology overview for CellSage, and the same for our adaptive remaining useful life estimation software, ARULE. Towards the end of the webinar, we'll start out by looking at an overview of the BDPS tool suite, and then we'll go over some future work and collaboration opportunities that we're pursuing with industry and academia, and then we'll provide an overview on some recent publications, a summary, and a Q&A. So, taking a look at some of the background on Ridgetop Group and our long-standing partnership with Idaho National Laboratory, or INL, we've been working closely with INL and Dr. Kevin Gearing, who's a distinguished staff scientist, for nearly 10 years. INL is a part of the U.S. Department of Energy's National Laboratory Network and is located out in Idaho Falls. Not only are they one of the nation's top labs for advancing lithium-ion battery research and clean energy technology, they've also been leading the nation in nuclear energy research and development. At Ridgetop Group, we are a trusted leader in developing hardware, firmware, and software solutions for condition-based maintenance, prognostic health management, reliability engineering, and our mission is to enhance safety, efficiency, and operational performance for both government and commercial applications while reducing maintenance and sustainment costs with innovative technology. Our work with INL started out with some of the aerospace work we were doing for looking at power supply prognostics, and naturally had some overlap with backup battery systems and UPS systems. And here at Ridgetop Group, we were established in the year 2000, and we are headquartered in Tucson, Arizona. We specialize in engineering design services, circuitry for harsh environments, and the development of advanced prognostic solutions across aerospace, defense, transportation, energy, and industrial sectors. With over 20 years of experience, Ridgetop Group has continued to set the benchmark for reliability and health management solutions, and we're also proud to be an AS9100D and ISO 9001 certified facility. So here on this slide, we have the problem description for why certain customers need our collection of tools. So those groups of customers include battery manufacturers, integrators, and researchers. And we really focus on three key elements of the lithium-ion battery life cycle, and that's circled in the red on the image in the upper right. So throughout the lithium-ion battery life cycle, it starts with the mining and refinement of raw materials, cathode production, battery design and manufacturing, battery first use, and battery second use before they end up in the landfill. And there's elements of this in terms of creating a circular economy for direct recycling of raw materials and having certain processes to advance and extend the life of these technologies. So here at Ridgetop and Idaho National Laboratory, we've developed a collection of tools that again really focus on the battery R&D phase during battery manufacturing and battery first use, and then using our collection of tools to help make informed decisions and diagnostics for second use applications. And some of the pain points that we address with our technologies and engineering services include decreasing time to market for new battery designs and new chemistries, optimizing BMS charge and discharge protocols, helping customers hit product warranties when they're integrating different chemistries into a product, and then also helping advance the capability for electrolyte modeling, as well as cycle life testing capabilities. And then with our ARULE software, we also look at the diagnostic capability and state of health estimation from a non-traditional context for lithium-ion batteries. So together, each of our tools help improve safety, reliability, and time to market, and that is captured here. Here we have a brief intro on each of the tools in this collection of MS&A, and that includes the advanced electrolyte model, which is used for optimizing electrolyte formulations during new battery designs. CellSage, which is a patented modeling tool for looking at battery degradation and dominant aging mechanisms such as loss of inventory or loss of active material. And then ARULE, or the adaptive remaining useful life estimator, which is a prognostic reasoner that helps us determine battery state of health and remaining useful life based on arbitrary types of feature data. So whether we're looking at rise of internal resistance or a spike in temperature or current or voltage, those are types of feature data coming from a BMS platform that can be processed by ARULE. We also offer a collection of engineering services for hardware, firmware, and software design and development. So next, I'll turn it over to one of our battery simulation engineers, Basad Goswami.
Thank you, Wyatt. Before we dive into the details of our simulation tools, I want to take a moment to discuss why simulation is so important in battery development. First, simulation significantly accelerates the development process. Instead of relying solely on physical prototypes, we can rapidly test and validate multiple designs in a virtual environment. This means we can explore a variety of ideas and materials much faster than traditional methods allow. Second, simulation is cost efficient. It reduces the need for expensive lab testing and physical experimentation, which not only saves on material costs, but also frees up resources for other parts of the development process. Third, it helps us mitigate risks. By simulating real-world conditions, we can identify potential failure points like thermal runaway long before the product its physical testing. This greatly enhances the safety and reliability of our designs. Fourth, simulation allows for optimization and customization. We can tailor battery designs to specific applications, ensuring the best possible performance in everything from electric vehicles to grid energy storage systems. Finally, simulation gives us data-driven insights. By generating detailed performance predictions, we can make more informed decisions about how our batteries will behave over time, helping ensure that they meet real-world demands. So as we can see, simulation is indeed a crucial part of modern battery development, and we are excited to show how our tools fit into this process. I want to emphasize the comprehensive scope of our battery simulation tools, covering every aspect of battery development and all the scales of it. Let's start with AEM, the Advanced Electrolyte Model. Here we focus on the molecular level, where AEM allows us to predict the properties of electrolyte compositions such as conductivity, viscosity, ion association, and so many much more. By simulating and optimizing the chemistry at this fundamental level, we can accelerate the discovery of materials with the best possible performance for a wide range of applications. Now, moving up to the cell level with CellSage. With CellSage, we model the aging and degradation of individual cells and even strings of cells. This tool allows us to simulate how different duty cycles and operating conditions impact battery life, providing detailed insights into how cells perform over time. This is key to ensuring that batteries remain efficient, safe, and reliable throughout their cycle. Finally, we arrive at ARULE. This software focuses on real-time diagnostics, allowing us to estimate a battery state of health and remaining useful life with precision. ARULE takes the data from individual cells and systems and translates it into actionable insights, helping end users know exactly when a battery needs maintenance or replacement. Together, these three tools, AEM, CellSage, and ARULE, gives us a complete picture of battery performance from the molecular scale to real-time operational insights. This means we cover every part of the battery development and monitoring process, ensuring that batteries are designed, tested, and maintained for optimal performance and longevity. With that foundation in place, let's dive deeper into each of these tools, starting with an in-depth look at the AEM through this video.
Batteries are becoming more abundant in our everyday world. They power everything from cell phones to electric vehicles to grid-scale storage for renewable energy. Battery design must be tailored to each application to optimize performance, longevity, and the product's weight. To this end, Kevin Gehring, a distinguished Idaho National Laboratory scientist, created Advanced Electrolyte Model, or AEM.
AEM is a molecular-based computer simulation program for discovering and optimizing electrolyte formulations in batteries to improve battery performance.
With AEM, researchers can determine over 100 property metrics virtually. It allows changes to the profile of a battery on the molecular level without having to build a prototype. By accurately predicting the performance of complex electrolyte formulations, AEM helps developers produce an efficient battery system and reduce energy storage costs. AEM can help capture and store renewable energy from sources like wind and solar more efficiently and at varying conditions. AEM also provides time and cost-saving benefits to accelerate electric vehicle and grid-scale battery system development.
AEM provides vast possibilities with over 50 solvents and nearly 40 salts. This creates millions of combinations, enabling users to find ideal candidates for their specific needs while considering the merits of various electrolyte options.
Each AEM analysis generates more than 20 reports, covering aspects like transport, thermodynamics, physical properties, thermophysical, kinetic, molecular, and macroscale metrics. This comprehensive information empowers researchers to make well-informed decisions on battery chemistry.
AEM's extensive predicted property sets span broad ranges of composition and temperature and are crucial for understanding battery electrolyte performance. Over 100 property metrics are generated and reported with each simulation. This includes ionic transport functionalities, thermodynamic and thermophysical terms, properties tied to molecular processes at interfaces such as lithium desolvation, electrolyte permeation into electrodes, and many more. AEM significantly accelerates battery development, bringing advanced battery applications to market more quickly.
Success of AEM can be seen by its increased adoption, where several large corporations and universities have licensed AEM to help accelerate their battery programs. The Advanced Electrolyte Model, helping create a world powered by clean energy.
Okay, let's take a closer look at AEM now, our advanced electrolyte model. AEM is a powerful molecular-based chemical physics software designed for electrolyte solutions, most often used in battery electrolyte screening and optimization. What sets AEM apart is its ability to make genomic-level predictions across more than 100 property metrics in each simulation. This means that it covers everything from molecular interactions to macro-scale properties, giving us a complete picture of how different electrolyte formulations will behave under various conditions. AEM supports a wide range of electrolyte components, and this library is constantly growing. Right now, we have access to over 50 solvents and nearly 40 salts, which allows us to screen and optimize virtually any combination we need. And it's fast. Most simulations run in under 10 seconds, even when covering thousands of different conditions. For more complex optimization tasks, it may take a little longer, but the scale is still remarkable considering the depth of data it produces. Customization is also a key feature. AEM allows users to define formulations with up to 10 solvents and 2 salts in each mixture, with broad ranges of salt concentrations and temperature. This flexibility lets us tailor simulations precisely to our needs. When it comes to accuracy, AEM maintains an impressive average deviation of just about 5% from lab data for many of its predicted terms. This level of precision makes it an incredibly reliable tool for real-world applications. Finally, the outputs are robust, meaning each simulation generates over 20 reports organized by property categories, providing an in-depth understanding of the electrolyte behavior across different metrics. In summary, AEM offers unmatched speed, accuracy, and versatility for electrolyte screening and optimization, making it a vital tool in the development of next-gen battery technologies. Now let's take a look at the wide range of outputs generated by the AEM. These outputs cover a broad spectrum of electrolyte properties, all of which are essential for understanding and optimizing battery performance. Starting with transport properties, this category includes key metrics such as ionic conductivity, diffusion coefficients, which are critical for predicting how well ions move through the electrolyte. Next, we have thermodynamic properties. This includes essential details on activity coefficients, osmotic pressure, and enthalpy, helping us understand the stability and behavior of the electrolyte under various conditions. Moving on, thermophysical properties like density and thermal conductivity, allowing us to evaluate how the electrolyte will respond to temperature changes, ensuring its suitability for different operating environments. Then we have rheological terms which deal with viscosity and flow characteristics. These are crucial for understanding how the electrolyte behaves in both static and dynamic conditions. Then we have ion solvation terms, which are also critical, giving us insights into how ions interact with the solvent, including solvation numbers and ion pairing tendencies. Then we have permittivity terms, focusing on the dielectric properties of the electrolyte. And finally, there are other categories that include specific electrolyte features such as surface tension and electrochemical stability. All these outputs are calculated as functions of concentrations and temperature, with a general concentration range up to 7 molal salt and temperature between -40 degrees C to 80 degrees C. AEM provides over 20 detailed reports per simulation, offering a comprehensive view of the electrolyte's performance across all these critical properties. Next, I would like to highlight the accuracy of AEM by showing its validation against some of the literature or experimental data from various studies. In this slide, we have several plots that demonstrate the model's performance in predicting key electrolyte properties across different systems. As you can see, AEM consistently shows excellent agreement with experimental data. And this level of accuracy makes AEM a highly reliable tool for both research and industrial applications. The model has been validated across a wide range of solvent and salt combinations, demonstrating its versatility and robustness. Whether we are working with common systems or complex formulations, AEM proves to be a precise predictive tool, helping to reduce the need for extensive experimental trials. Here we demonstrate how AEM outputs can be seamlessly integrated into Newman-type transport models, which are widely used to predict battery performance. These models simulate how electrolyte properties change over time and across different parts of the cell, allowing us to understand concentration, polarization, and overall cell behavior. AEM provides key electrolyte properties which serve as essential inputs to these models. By feeding these accurate and detailed outputs into Newman models, we can better estimate battery performance under various conditions and cycling profiles. This integration between AEM and Newman-type models enables us to bridge the gap between electrolyte formulation and real-world battery performance, giving us deeper insights into how different electrolyte compositions will impact battery efficiency and longevity. Now I'll move forward to a quick demonstration of the AEM graphical user interface. So this is in general how the AEM GUI looks, and I will give a brief overview of each of the tabs. So initially we have to select whether we want to move forward with a single fixed composition of solvents, or we can also choose a larger matrix for optimization of electrolyte formulation. Then the next tab, we have to select the number of solvents and the salts, and also we need to specify whether the composition should be with respect to volume or mass. Another important inclusion into the AEM was the inclusion of ACCC module, that's the arbitrarily chosen chemical compounds. So this allows users to define their own solvents and also for salts. So we have this ACCC for solvents and salts, and this is particularly useful for research groups who want to develop their own solvents and want to create an electrolyte based on that. And we have included this feature in our AEM as well. Next comes the temperature settings, the triple ion stability, and other factors like the electrolyte ingress, the escape calculations, and the double layer calculations. Finally, when we hit run, of course, as I mentioned previously, it takes less than 10 seconds for each of the runs. And of course, for larger matrix calculation, it takes a bit more. But there are various ways by which we can visualize the results, whether you can go for text, you can choose various plots. So here we see, like for a particular case study, like for specific conductivity over concentration, this is a 2D plot, and we have the feature that this data can also be extracted to CSV, where users can use them for further analysis, and if they want to compare the modeling results with experiment, that can also be done. Another great inclusion in our AEM model is or particularly the GUI, is the inclusion of the 3D plot. This offers great qualitative insights about each of the parameters and the physics behind them. Like, for example, specific conductivity. We know that specific conductivity in general, it increases with temperature. And with the help of this 3D plot, you can visually see that how the specific conductivity increases over temperature, and also how it depends on the molality or the concentration profiles. Then we move on to the one of our latest development, that's the AEM Python API. This is a great additional capability that has been provided to AEM users. The AEM Python API enhances the flexibility and usability of the AEM platform by allowing users to create, manage, and simulate electrolyte compositions directly from their Python scripts. This API is designed to work seamlessly with AEM command line interface, providing as much more customizable and automated approach to electrolyte analysis. One of the key strengths of this API is its ability to leverage the extensive AEM compound library. It includes both ACCC and non-ACCC solvents and salts, giving users access to a wide range of compositions for their simulations. This means that whether you are focused on electric vehicles, grid storage, or other applications, the API can support you in modeling the best electrolyte combinations. Additionally, the API streamlines the workflow by combining results from different simulations into easy-to-read reports, which can be automatically saved in CSV format. This makes it incredibly convenient to track key properties like density, viscosity, conductivity, and even ion association populations. And if you are a fan of data visualization, the API has built-in tools for generating graphical plots to give you deeper insights into these properties. In short, the AEM Python API brings a new level of control and efficiency to electrolyte modeling, making it an invaluable tool for researchers and developers working to push the boundaries of battery technology. With this detailed overview of AEM, let's move forward to our next set of tools, and I would hand it over to Wyatt.
Excellent. Thank you, Basab. Great overview. Yeah, thank you again, Basab, for providing such an in-depth look at AEM. This technology has truly been instrumental in our company's growth, and our exclusive partnership with Idaho National Laboratory has unlocked this unique capability to be utilized around the globe by major battery manufacturers and Fortune 500 companies. On this slide, we'll focus on the operational envelopes for battery applications, which has a direct relationship to our next technology, CellSage. So battery usage across multiple domains can be incredibly complex due to the dynamic duty cycle and environmental stress factors encountered over the battery's operational life. And as we know, over time and cycles, the usable power envelope tends to shrink. Not only does that usable power envelope tend to shrink, there are also complicated paths for dominant aging mechanisms such as loss of inventory and loss of active material. Several processes such as SEI formation, gas formation, and the incomplete electrode wetting or electrolyte dryout can cause things such as surface and void space blockage, which have direct impacts on LLI and LAM with pore blockage. And then it also leads to higher local current densities and other key activities such as particle cracking or separation. So to address these failure modes and activities, we've developed our CellSage battery health modeling and simulation software through our original research and development work done with Dr. Kevin Gearing at INL. Here we have a brief overview of that technology. Excellent. So that video provides a brief introduction on CellSage, but it doesn't necessarily cover all of the family of modeling tools that this technology fully encompasses. So here on this slide, we can see a collection of different modeling capabilities that have been in design and development for nearly 20 years. So this starts out with things like the kinetics module, which was the foundation for some of our early work with the Department of Energy Vehicle Technologies Office. We later expanded upon that to include the CPC module for capacity, power, and conductance. And then through our work in working with industry partners and researchers, we started looking at dynamic duty cycles, which led to the design and development of the DCC module for detailed cycling conditions in closed-loop systems such as autonomous vehicles, robotic systems, or even unmanned aerial vehicles. And the most recent body of work is surrounded by the TAA module for transient analysis, and it's a materials-driven approach to look at what we call an autonomous model for later life predictions based on very detailed parameters around the electrolyte formulation and design details around the anode and cathode properties and the form factor and the unique capabilities. So this is really taking CellSage into the future with the TAA module, where we'll be looking at a purely materials-driven electrochemical model where the combination of the kinetics, CPC, and DCC, or even the LMD model is a combination of data-driven, physics-based, and AI machine learning capabilities. So the TAA module, again, really allows us to take this technology into the future with the first of its kind electrochemical model accounting for everything from the electrolyte formulation all the way to the cell properties based on our collective work with the advanced electrolyte model and CellSage. So what is CellSage in kind of a general context? And CellSage is an advanced battery and cell aging software simulation tool that is designed to access how various battery chemistries age and degrade in response to different usage conditions, stress factors, and how they are deployed in certain systems or subsystems or products. And CellSage allows us to go beyond the basics of looking at key failure modes. It also calculates over 20 vital health metrics and aging effects, including the state of charge, capacity loss, cell and battery conductance loss, and also power fade. So this leading edge simulation platform allows our end users to create what-if scenarios and evaluate the impact of operational and environmental stress factors based on battery performance, as well as the optimization of charge and discharge protocols for a unique BMS strategy or a charging station. The technology is also offered as a cost-effective solution to help optimize cycle life testing capabilities and diagnosing issues in historical cycle life testing data that may already be collected. So the DCC module, we touched on it when we were looking at the family and modeling tools for CellSage. It stands for detailed cycling conditions. And this unique capability really allows us to look at very detailed steps associated with a duty cycle. So whether it is for an electric vehicle, a grid energy storage system, a string, pack, or module level, we can look at the different charging steps associated with that and simulate the effects of cycle life and calendar life aging for that particular cell and string. So some of our ongoing research is to extend that capability to the module and larger system level when looking at larger systems such as a complete electric vehicle or hybrid electric vehicle. Some of the typical input parameters are things you would expect, including the cell chemistry, the simulation time, the SOC, the relative cycling severity in terms of how it relates to the baseline cycling testing data for the initial model development, and then the duty cycle, which is specified in great detail with the DCC configuration file, and then things like annual temperature profiles or constant temperature profiles for the deployed environment. So we have a capability to look at the annual temperature profiles in specific geographic regions. So we can do a 24-hour temperature extraction based on the monthly highs and lows of historical weather data in a particular city or region. This also allows us to investigate whether a thermal management system is needed and whether or not daily thermal cycling impacts a given set of aging conditions or aging paths for that battery. And then we can look at thermal hotspots with our stream analysis in kind of a best case, worst case scenario. We can also provide customized testing services or model development through our partnership with Idaho National Laboratory. So here on this slide, we can see a partial list of some of our data outputs. So this includes things like the capacity loss and the fraction of capacity loss versus weeks or cycles. So if we're looking at the loss of lithium inventory or loss of active material, that can be differentiated based on the underlying SRE models or signal rate expression models, which we covered in our webinar last month. We can also look at things like ohmic resistance, net ohmic heat, the fraction of effective discharge power, which is a very useful metric when looking at whether or not a duty cycle can be carried out based on not just capacity loss, but the actual duty cycle that we're trying to achieve. Some of the battery chemistries that we have in CellSage, there's a set of defaults based on our research over the years. So this includes cells from Panasonic, Sanyo, A123, some DOE specifically tested cells, which were based on an NCA graphite cell chemistry, Altio, Alamo, lithium cobalt oxide, as well as several others with our addition of the new chemistry import feature, which we covered in previous webinars over the past couple of years. So that capability has really allowed us to take CellSage to the next level in terms of being able to easily import existing baseline testing data for cycle life and calendar life aging and generate new models for new chemistries and new customer applications. So it's been instrumental in that regard. And that's kind of captured here with the new chemistry import feature and the model correlation. So here we can see the 4 required baseline testing data sets. So the top 2 are representative of cycle life testing data at 2 different temperatures, 25C and 45C in this case. And then we have calendar life aging based at 45C and 55C And what these 4 data sets allow us to do is automate the regression analysis for determining the sigmoidal rate expression model parameters, and then calculating the activation energies, which is, as we know, temperature dependent for this type of physics-based model that we have with CellSage. Here we have an example simulation for an EV case study where the LFP cell, which was manufactured by A123, we did some testing and modeling and simulation for a battery system with and without a thermal management system invoked. And here, as we expect, the plot on the left shows a very wide variation in capacity loss, whereas the plot on the right shows a more uniform aging pattern based on the cycling conditions observed by this particular duty cycle. And as we expect, when you have a thermal management system in place and enabled, you're able to maintain a steady operating temperature for the cells at the string, pack, and module level. So not all systems do incorporate thermal management, and it is, as we know today, most or I would say probably all electric vehicles have a good thermal management system in place. But smaller things like consumer electronics or even golf carts, those are really exposed to the elements, and even certain robotic tools that are used out in industrial environments. So having a thermal management system involved is really a design trade-off decision for battery integrators, and this unique capability allows them to evaluate that, as well as what is the most optimal lower and upper limit to optimize for maintaining the life of the battery, but also not consuming enough energy to deplete it from the application it's intended to be used in. And here we have an example of CellSage being used as a diagnostic capability. And this was with one of our robotics customers that we were working with. And something that was unexpected when we were looking at some of the cycle life testing data was that the 20-watt pack was showing a larger increase of capacity loss versus a 40-watt pack. So this was for a 4S1P pack used in a robot autonomous system. And we were able to showcase the diagnostic capability, because if we look at the dash line on the bottom versus the solid line on the top in red, the dash line on the bottom shows what the capacity loss should have been had there not been a deviation in the test plan during cycle life testing. And what happened was, around 700 cycles, the customer actually had stopped resting the cells during this testing capability, which invoked a polarization hysteresis effect to happen in this cell. So that was only observed in the 20-watt pack. And by adding that as one of the SRE terms in this model, we were able to not only replicate it, but also show them the effects of reversible and irreversible aging. And in both cases, there were savings for an optimization of the capacity loss for this testing capability, which helps customers understand their warranty periods for certain products and systems. And here we have an example from a recent publication where we were looking at long duration energy storage and how we were able to utilize the physics-based elements of CellSage to generate an initial set of predictions for long-term duration energy storage. So CellSage today kind of operates on having baseline testing data for a known period of test or end of test, but you can generate what-if scenarios for later life predictions, and that's kind of captured here with the dash lines after the known end of test time frame. So we have a publication that we can share that kind of captures how we used Monte Carlo simulation, and we're able to, and different machine learning and deep learning techniques to do later life predictions based on generating a family of predictions based on the underlying sigmoidal rate expressions and outputs from CellSage. So whether we were looking at the decline of state of health, capacity loss, or power fade, this approach can be applied. And here we'll see kind of a brief example of how the tools can actually work together. And next month we'll go into a little bit more detail on that. But on the left we have some data outputs for a best case, average case, and worst case scenario for the fraction of capacity loss outputs from CellSage, and how we can process that with our adaptive mean use life estimator ARULE. And ARULE enables extended common-like filtering on curvilinear data, which is correlated to a failure mode, and then we can process that data to determine state of health, remaining useful life, and prognostic horizon according to an underlying PHM framework that we developed here at Ridgetop. So ARULE was originally developed for aerospace applications where we were looking at different failure modes, whether it be in power supplies, gearbox systems, electrical or electromechanical systems. It is agnostic to the type of feature data that it processes, but feature data by definition is directly correlated to a type of a failure mode in a given system or subsystem. And here with our collection of battery modeling and simulation tools, we found a growing application and use case for looking at different types of feature data from a BMS system, or even hardware in the loop types of simulations where you can look at capacity fade or internal rise of resistance or other BMS data streams and variations from those data streams, and process that with ARULE to determine SOH and RUL in a closed loop environment. So it's very useful for looking at that and also investigating state of health estimation methods. So I touched a little bit about on the integration of the different tools. So next month we'll be doing a webinar on what we call the Battery Diagnostic and Prognostic System Tool Suite, or BDPS Tool Suite. And this is a active product development effort that we are doing through our most recent Small Business Innovation Research Program, or SBR program, where we have developed a modeling and simulation and data acquisition framework to keep track of battery degradation data during initial applications such as a grid energy storage application, or even cycle life testing capabilities, and then keeping track of that data to have a model feedback and making informed decisions for second life applications. So with this, we'll be introducing some capabilities for real-time battery health monitoring and diagnostics, as well as the prognostic element when processing, model data versus a BMS acquired data stream, and comparing that with ARULE to do things like fault detection and isolation. So this is a very similar technology and framework that we've been applying based on our application and participation with IEEE Reliability Society in the design and deployment of prognostic health management solutions at a larger system level. So Ridgetop has a few different team members actively participating on the standards committee, showcasing these types of projects with the BDPS tool suite, as well as our industrial IoT sensing system, Sentinel Motion. So here we can see a system overview of the BDPS tool suite, where you have a battery pack and a BMS platform deployed in a given system. So in this case, it is an electric vehicle, but it could be a stationary backup system, or it could be a larger collection of grid energy storage systems that are all distributed. And with that, in some cases, you have historical battery aging data, and we have developed some hardware, firmware, and software interfaces based on our collaboration with utility companies and EV manufacturers to sense, acquire, and offload this data and compare it against some of our models within the BDPS tool suite. So that includes CellSage, the DRDM, as well as some additional models and derivations that we've been developing for specific customers. And again, as you compare real-time BMS data against your model data, you're able to make informed on-demand decisions based on that deviation from a known healthy baseline versus what is actually going on in the field. So here we have kind of a brief overview on the IEEE 1856-2017 PHM standard, and this is always good to show for the BDPS tool suite because it really captures the core PHM operational processes and the functional blocks that we are working to implement for our specific customers in the utility market segment as well as the EV market segment. So it starts out with your sensing and data acquisition, your data manipulation and pre-processing and feature data extraction methods, which then allow you to do your state detection, health assessment, and prognostic assessment with tools like ARULE. And again, as you have those deviations from a known healthy baseline versus your system or the field data, you can make advisories and health management actions based on this architecture. So again, we're applying the same architecture in our industrial IoT system, but here with the BDPS tool suite, we're applying it for a different set of challenges with understanding battery degradation and also capitalizing on our strengths with and partnerships with Idaho National Laboratory and our collection of battery health modeling and simulation tools. So here we have just some key points on the value of the different tools. So again, in the EV market segment, we're able to offer significant cost advantage compared to expensive empirical data collection techniques. We're able to optimize BMS charge and discharge protocols, decrease lifetime testing, and we also have some of our patents shown here, which provide some good background information on the underlying modeling framework developed over the years. CellSage also, and AEM now, which we'll be announcing in the coming weeks, has a number of different awards based on the ongoing work we've been doing around the globe, again with major battery manufacturers, researchers, and Fortune 500 companies. So if we look at some of our use cases with different customers, we have several different publications. I believe with AEM in particular, we were over 30 plus publications and growing every week. So just got a few more that were published just recently. But here we can see in the bottom left a critical evaluation of the advanced electrolyte model that was done with Eric Logan and Kevin and Jeff Don and Aaron here. And with this body of work, it was really about the validation of AEM and key outputs over a wide range of temperature conditions. And to date, AEM is one of the only electrolyte modeling tools that has been this thoroughly tested and evaluated. And a lot of the work here was done by with Jeff Don's group at Dalhousie University, and there are several publications based on the collaboration with him and Kevin at INL dating back several years. And on the right, we cover that in a little bit of detail with the robotics industry, where we're utilizing CellSage as a diagnostic tool to look at the difference between a 20 watt and 40 watt pack during cycle life testing, which then help that particular customer optimize their charging discharge protocol and their warranty periods. So we're getting pretty close to the end here. This is kind of just an overview of our core team members. So myself, Basab, and Dr. Kevin Gearing are shown here. We also maintain a staff of highly skilled data scientists and engineers and domain experts in the fields of reliability engineering, prognostic health management, and battery modeling and simulation. We also have a dedicated sales rep network with a global reach in North America, South America, Europe, and Asia. So if there are new collaboration opportunities or interest in this technology, we encourage you to reach out directly, or of course reach out to our local sales representatives in your region. So that is located on our websites and on theirs as well. In summary, today we kind of covered the different technologies within the collection of Ridgetop's battery modeling and simulation analysis software tools. So this includes AEM, CellSage, and ARULE. And again, the goal of these technologies is to provide a proven methodology and framework for electrolyte modeling, and as well as diagnosing and predicting battery performance and aging over arbitrary conditions, and understanding how we can help customers improve their battery design, whether it's through electrolyte formulation and optimization, or cycle life testing, or charge and discharge optimization for their unique duty cycle or system. The technology allows us to look at a wide range of battery aging trends in different systems. So whether it's electric vehicles or grid energy storage, we've done a number of different projects in both market segments, as well as a wide range of consumer electronics and aerospace applications. The technology allows us to look at complex aging profiles and dominant aging mechanisms in lithium-ion batteries. And we've also started looking at other types of battery systems for solid state, as well as redox flow types of systems. So that's part of our ongoing work and research with different industry collaborators. And yep, the last bullet point there is just about how this collection of tools and the design and development of the BDPS tool suite helps our customers understand battery second use applications, again, by understanding that first aging profile and what types of optimization strategies can be applied for a potential second use application. All right, so I think that covers it. We'd now like to open it up for any questions that may have come up. Let's see here in the chat.
I was wondering, how does the accuracy of simulations compare to real-world battery testing results?
Yeah, so that's a great question. So depending on the type of data, whether we're looking at electrolyte properties or cycle life testing data with CellSage, we're able to compare the actual lab and test data against our model predictions. So in the case of AEM, we touched a little bit on the comparisons and evaluation with Jeff Don's group, but it has been done with several other collaborators in different universities for the wide range of electrolyte properties. And on CellSage as well, we touched on that in our webinar a couple months ago, where we were able to showcase the accuracy evaluation of each of the 4 data sets for the default models in that framework. So between that and the publications and the software comparison capability, we demonstrated a wide range of reproducibility, and that is furthermore captured in the patented and copyrighted modeling techniques for AEM and CellSage.
That's great. Thanks a lot.
I have a question. In what ways is AI being leveraged to improve the speed and efficiency of simulations in the battery modeling?
Yeah, so that's a great question. So I'll kind of touch on that in the context of CellSage, but Vasant, maybe you can kind of elaborate on it hereafter. So the different AI machine learning methods we kind of touched on when looking at, so I can get back to that. This slide here for doing long-term energy storage predictions. So we're using a combination of physics-based models and machine learning techniques to do longer-term energy storage predictions for the capacity fade. And in this case, again, it's really taking it to more of a hybrid modeling approach, which is something we've done a few publications around. So this is kind of the context in which it's being applied for CellSage, but there are also elements and different techniques being applied on things like thermal management or even electrolyte optimization. That is part of an ongoing work we're doing with our different collaborators.
Thank you.
Hey, so I was just wondering, how easy is this software to really get somebody up to speed on using it? Like, what kind of qualifications or understanding of the batteries do people really need to have to use these tools?
Yeah, that's a great question. So yeah, historically, there's definitely a steep learning curve in trying to understand and deploy some of these tools. But what we've done through our partnership with Idaho National Laboratory is make each of these tools intuitive and have common training methods and frameworks. So we have a collection of training tools and documentation and examples, and again, the growing list of publications with our different research partners and universities has really allowed the learning curve to be overcome. And this is true for all of these tools. So again, our partnership with Idaho National Laboratory is one of the first of its kind within DOE, and it shows the value of taking cutting edge innovation coming out of the national laboratory system and leveraging key industrial partners such as Ridgetop to test and validate and deploy this technology in real world applications. So in going through this process over the last several years, again, nearly 10 years here, we've been able to really refine and add a lot of customer value for each of these tools.
All right, thanks.
All right, so I think that covers all of the questions that we're seeing here. I'm not seeing anything here in the chat, but yeah, if there are any additional questions, we do encourage you to reach out to us through our website. And again, we'll be uploading these slides on our YouTube channel for further review. And we do look forward to having further discussions, based on any feedback or ideas you may have. So thank you again for your participation, and we look forward to discussing how we can work together. Thank you.